Hello again. We are on the last part of Module 11, where we are going to talk about an F-test in simple linear regression, and we're going to look at some computer output and what is called an analysis of variance table. Besides the t-test, which we've already looked at, there's another test called the F-test that can be used to test a two-sided hypothesis test on the slope term. That is, it can test the hypotheses is beta 1 equal to 0 or is beta 1 not equal to 0. However, the F-test cannot be used for a one-sided test for some technical mathematical reasons that we don't need to be concerned with. Now, exactly what is an F-test? Well, the F-test is going to use the following ratio as a test statistic. F is equal to MSR over MSE. We've already looked at MSE before. MSE, remember, is SSE over n minus 2. SSE, the sum of squares due to error. If you go back in your notes, you should find that in the problem we've been doing, the grades and hours of study problem, SSE was 398.25, n minus 2 was equal to 4, so that gives us an MSE of 99.56. Now, what is MSR? Well, like MSE, MSR stands for mean square regression, and that's going to be equal to SSR divided by the regression degrees of freedom, which turns out to just equal 1. It's the same as the number of independent variables. So MSR would be SSR over 1. Again, earlier we had SSR to be 1201.75. So that gives us MSR as 1201.75. And so our F statistic for the problem we've been doing, MSR over MSE, 1201.75 over 99.56 is equal to 12.07. Now let's take a closer look at the F statistic here. Go back to our F ratio. In mathematics, you can show that if the null hypothesis is true, if there is no significant relationship between these variables, then MSR and MSE should be about the same, in which case this ratio would equal 1. On the other hand, if the alternative is true, if the slope is not equal to 0 and there is a significant relationship, then MSR, the explained variation, should outweigh MSE, the unexplained, and therefore this ratio would be greater than 1. Therefore, we're going to want to reject the null hypothesis and conclude the alternative for a larger F value in the right end of the distribution. That is, we're going to have what we'll call a right-tailed test. We'll always reject the null in this particular F distribution in the right end of the distribution. Now, we've got the calculated F statistic. We need a critical value, and we'll get that off of the F distribution. The F distribution looks a little bit like a chi-square distribution, which we covered back in Module 9, I believe. It tends to be somewhat positively skewed. Again, the F distribution is a little different than anything you've seen before in the course. It's identified by both its degrees of freedom in the numerator and in the denominator. So the F ratio that we just looked at has 1 degree of freedom in the numerator, the number of independent variables, and in the denominator it has n minus 2, which in the problem that we've been doing, n was 6, so n minus 2 is equal to 4. Here's just a very small portion of the F table that is very likely in the back of whatever textbook you're using. You look up degrees of freedom in the numerator and degrees of freedom in the denominator. So I just gave you the ones for the particular problem that we are doing now. We have 1 degree of freedom in the numerator and 4 in the denominator. You're just given a few limited probabilities that you can look up as your alpha level. These are the areas in the upper tail of the F distribution. You can look up a 0.1 or 10% area in the upper tail, 5%, and so on. We're going to use the 0.05 in the problem we're doing now, and that would give us a critical F value of 7.71. That is, With 1 degree of freedom in the numerator and 4 in the denominator, an F value of 7.71 leaves a probability of 0.05 in the upper end of the distribution. So let's put it all together into our hypothesis test. Our hypotheses, which we've already stated, is beta 1 equal to 0 or not. We'll use the standard 0.05 level of significance. We've already calculated our F statistic to be 12.07. We're only going to use the critical value approach here because of our limited alpha levels and the F table. It's harder to find p-values. We're going to reject the null hypothesis if we get an F ratio greater than 7.71. We already know that our calculated F is 12.07, so we do reject the null hypothesis. And therefore we conclude that there is a significant linear relationship between grades and study hours. Here's a little graph of approximately what the F distribution looks like. As I said before, it's positively skewed. Our critical value here was 7.71 with 1 degree of freedom in the numerator and 4 in the denominator. 7.71 leaves a probability of 5% above it. Our calculated F ratio is in the rejection region, so we reject the null hypothesis. There's something we need to be careful about now that we've covered significance tests. For example, both the T and F tests here indicated that we do have a significant relationship between our X variable and our Y variable. Does that mean that changes in your X variable cause changes in your Y variable? The answer here, of course, is no. The test can show significance, but causality really comes from theory and underlying theory. Now, in the example we used, where we had grades as a function of hours of study, I would imagine that there's quite a bit of educational theory that would support the idea that more time on task, that is more hours of study, should lead to higher grades. And therefore our statistical test can be seen as lending some support to that theory. But again, it's not a proof. You've all heard the expression that correlation does not imply causation. We can find statistically significant correlations for lots of variables where there is no causality between the variables. So causality is a little bit more difficult to get at. Okay, we also want to look at a computer printout. Besides doing a lot of the calculations on a TI-83 or 84, regression can also be done on various computer programs such as Excel. If you're familiar with Excel, open up an Excel spreadsheet and put your two variables in columns. Here we're going to take a look at it. Here's our two variables that we've been using throughout this example, grades and hours of study. Now, if you want to do regression in Excel, when you click the Data tab up here, you're going to need something over on the right called Data Analysis. If it's not there, you very likely will have to add it in to your Excel program, and you do that by clicking the File and menu button, go down to Options. On the left-hand side, notice something called Add-ins, and you double-click that. At the bottom, it says Manage Excel Add-ins. Click Go. And notice the very first one that says Analysis Tool Pack. You need a check mark in that box. I've already got mine there. So put a check mark there and say OK. And then when you click the Data tab, you should see this Data Analysis over on the right. Now, to do your simple regression on these two variables, click into that Data Analysis tab and go down until you find Regression right there. Click OK. And the program is going to prompt you to enter your Y range of data. You can just take your mouse and drag through, which I've already done before, but let's do it again. Take your mouse and drag through the data, and that puts the codes in for where your Y variable is. Do the same thing for your x variable. We're using a 95% level of confidence, which is equivalent to a 5% level of significance. Just click OK at this point, and you're going to get all of this output. And I've already looked at the output, and now I'm going to go back to the same output in PowerPoint, where I've highlighted some things. Down at the bottom, we have our intercept and our slope term. We have the coefficients. If you go back in your notes to when we first calculated the regression equation, remember we had a slope term of 4.807, an intercept term of 41.34. Here are those coefficients for you. Here's our t-statistic that we calculated for testing the significance of the slope term, 3.47. I think we actually had 3.48, but that's just due to rounding. And here was our p-value, 0.0254, meaning that we could reject the null hypothesis for any alpha level above that p-value. In the middle, we have what's called the analysis of variance table, which calculates SSR, SST, SSE for us, converts them to mean square errors and mean square regression. And there's our F statistic that we just looked at a minute ago, 12.07. You'll notice that this significance level here is exactly the same as the p-value for the t-test. Remember I noted earlier that the f-test always gives the same results as the t-test in simple regression, so you'd have the same p-value. Finally, the last thing I want you to note up at the top here is r squared, the coefficient of determination. 0.751 we had as our r squared, meaning again that 75.1% of the total variation in our dependent variable is in a sense explained by the linear relationship between x and y. So you should be familiar with reading computer printouts like this and finding the important elements that you need. It's also, of course, much easier to use a computer program like Excel in calculating regression than it is to do all the calculations by hand. And that's the end of this module.